Hello everyone, in this lecture we are going to discuss another clustering algorithm known as the Gaussian Mixture Model or GMM. So Gaussian Mixture Model is an instance of much broader topic known as mixture models. In the machine learning literature. So in this lecture, we are going to discuss GMM, which is an instance of much broader topic known as mixture models in the machine learning literature, where in GMM, the underlying data distribution is modeled or approximated as a simple linear superposition of the Gaussian components of the GMM. So it can be used to model or approximate the multimodal distributions that generated a data set. So let's suppose if we have a data, so let's assume that we have a data set and this data set is generated from some distribution P of x where the data set contains m data points xi, where each of the xi is an n-dimensional real vector and I goes from 1 to m. That is, in this data set D, we have m data points where each of the data points is an n-dimensional real vector, and this data set is sampled from a distribution P of x. So there is an underlying true distribution. So P of x is the underlying true distribution which we do not have access to, but what we have access to is a data sampled from that distribution or generated from that distribution. So we can use the Gaussian mixture model to model or approximate the underlying complicated or perhaps a multimodal distribution that generated the true dataset. Just like what we did in the kernel density estimation. So in kernel density estimation, we had a dataset which is generated by some multimodal density function P of x, but we didn't have access to the true density function. What we had access to was a dataset sampled from that density function or that distribution. So we estimated that distribution using the kernel density estimator function, and then we found the modes of the kernel density estimator function, and then we use those modes to cluster data set. So similarly, we can do the same thing in the GMM. So we have access to the data set, but we do not know the true density function or the distribution function that generated this data set. But since we have access to the data set, we can use this data to approximate this underlying true density function or this distribution. So GMM is an instance of unsupervised machine learning algorithm. So all the previous clustering algorithms, the k-means clustering algorithm and the kernel density estimation based mean shift algorithm that we have learned are an instance of unsupervised machine learning algorithms. Similarly, the Gaussian mixture model here is also an unsupervised machine learning algorithm. So it's an unsupervised machine learning algorithm where, similar to k-means clustering or the kernel density estimation based clustering, the goal here is to identify the number of components or clusters in a given data set. So the goal is to identify the number of clusters in the data set D, and to also associate each of the m data points in this data set with these clusters. So the goal is to identify the number of clusters and have every data point in the data set associated with one of the clusters that we have discovered in the data set. So whereas in k-means clustering and the kernel density estimation which resulted into the mean shift clustering algorithm, we had hard assignment of every data point in a set to the associated cluster. In GMM, we can have a soft assignment where instead of saying that this dataset belongs to this particular cluster, we have probabilities with which the data point associates with a particular cluster. So in the k-means clustering algorithm, we had to specify the number of clusters to the algorithm. So the number of clusters k is an input to the algorithm, whereas in the mean shift clustering in the kernel density estimation, which resulted into the mean shift clustering, the number of clusters was computed automatically. And also every data point in the data set was assigned one of the cluster identities. So in both the algorithms, the data points are finally assigned their cluster identities, but in k-means we have to specify the number of clusters as an input to the algorithm. But in kernel density estimation based mean shift clustering algorithm, we do not have to specify the number of clusters. So k-means is a parametric clustering algorithm, whereas the mean shift clustering is a non-parametric algorithm. In GMM, we again have to specify the number of Gaussians in the Gaussian mixture model. So in GMM, similar to the k-means clustering algorithm, the number of Gaussian components in the GMM have to be specified. So the number of Gaussian components or the number of clusters or the number of Gaussian components is an input to the algorithm. So GMM is again a parametric clustering algorithm. It's an unsupervised but it's a parametric unsupervised clustering algorithm. So as I mentioned previously, in Gaussian mixture model, the underlying density function or the underlying distribution is modeled or approximated as a simple linear superposition of the Gaussian components. So Gaussian mixture model, as the name suggests, is a mixture of Gaussians. So a Gaussian mixture model has k different Gaussian components, where k is a hyperparameter. So the number of k denotes the number of clusters, number of Gaussians, which is equal to the number of clusters in the dataset. So we have to make a choice how many clusters we want to find in a dataset. So this number of Gaussians or k or the number of clusters is an input to the algorithm. So now that we have learned a basic definition of the GMM, we will now formally mathematically define what a Gaussian mixture model is.